Today we're talking about data centers. Why are we doing this? Well, let me give you a little context. Maybe you already know anyway, but I'm going to do it. I'm going to tell you anyway. As M&V people, we often, visit our buildings, and we should always be looking for other opportunities, because a lot of times our projects aren't performing as well as we want them to, and it's nice to provide some kind of, service to our clients by showing them, look, here's some other things you can do. You can do that, but also if you're falling behind on your savings, maybe you can point out other savings and maybe get your company to, invest in some really low cost, no cost measures that are going to help you, get over that hump and start actually meeting your savings guarantee again. So data centers are one thing that I guess you will see, going into more and more buildings. They put in data centers, all of a sudden energy usage goes up and all of that, but that also will bring in a lot of opportunities for energy savings. And it's good to just have a clue about data centers. And so with this, it's 1 hour. You're not going to become a data center expert, but in an hour, you're going to learn some real basics and know some basic things to look for. And maybe that will really help your clients. So with that's our intro. We're talking to Hannah Bastawrose. I'm sorry, Hannah, how do you say that?
You got it. It's spelled phonetically.
Okay. She used to be Hannah Seeger. That was her original name. She used to work at Train, and I believe you were a PDE, or you're an engineer of some sort in performance contracting. That I know. In fact, she will tell us about herself because she knows more than I do about it. So that's it for me. Hannah, go ahead.
Awesome. Thanks so much, John. So my background, I went to school for mechanical engineering, but came up through energy engineering, worked for several companies, Schneider, TK1SC, an MEP firm, and Train Technologies, and eventually started my own company, Itty Better. So I'll just go right into the next slide, because you may be wondering, does this girl just specify in data centers? Well, I'll just tell you the connection of what Itty Better does, and then where that connection kind of fits with data centers. So our slogan is, you make buildings better, we make you an Itty Bit better. And how we do that through process improvement and educational assistance for our peers. We specialize in energy, sustainability, and healthy spaces, and help engineers, contractors, M&V engineers, and alike in the space to assist you in making your workflow more efficient. Within that educational space, we are focusing our efforts in the data center industry because it's growing so much. There's so much data out there. All the companies want more and more data. And so we are focusing our efforts because they use so much energy. So take a look at the website, see if there's anything on there that you can use. Specifically for you guys on this call, M&V and energy engineers, you'll probably be most interested in our process improvement assistance. We know engineers love spreadsheets, and that's what we help with. Microsoft Excel and Power BI, assisting you in customization or improvement of the tools that you already created. We know you got your software, we know you got your favorite spreadsheets, and we just help make it an itty bit better. We also have a handful of other resources on our website that are curated for engineers to help you with your work, whether it's through site audit or doing the calculations and engineering themselves. We are a new company, so this list is growing, but go on, take a look, and if you don't see something that you would like, just feel free to reach out. We're always happy to see how we can help. So let's dive right into the subject of today, data centers. We are going to start with the absolute basics, talk about why we're talking about data centers, what makes them different than occupied spaces. As people, we live in occupied spaces, so we're the most familiar with that. and how do data centers differ. We're going to then look at how we can benchmark data centers, and then we're going to follow our favorite friend, the energy pyramid, and talk about different technologies that target each layer of the energy pyramid. And finally, I'll leave you with some further resources that you can use to dive deeper into the subjects that we're going to talk about today. So let's get started. So what is a data center? I know this is absolutely basic, but I want to bring everyone up to speed and on the same page. How many metaphors can I use? A data center is a centralized facility for an organization's IT equipment. It is used for storing, processing, and dispersing data and applications. So when we think of a data center, most likely we're thinking about the big picture on the right-hand side. Racks on racks on racks, lots of data centers and servers for a very large facility. However, the picture on the left, the more smaller, cozy data center is just as important to its organization as the large data center on the right. And so though there's a lot going on in these facilities, they are critical to the business. They also use so much energy, and we'll go into just how much energy, but this is why we're taking a look at these. So you may be doing your site walks and walking right past the data centers because a majority of data centers are small server rooms and closets serving small to medium-sized businesses. And there are over 3 million data centers in the US. So though its footprint in the facilities that we're walking through is fairly small, they are so energy dense. To give you an idea of size. So we're all probably familiar with our typical office. And as a rule of thumb, we probably see them between 3 and 5 watts per square foot of power density. But for a data center, we're looking at more like 5 kilowatts per square foot for a data center. And this number is growing, and surprisingly, this is actually on the lower side. So towards the end of the last decade, server rack power density was probably typically between 3 to 5 kilowatts per square foot. However, there was a survey done by the Data Center Knowledge, which is just an organization that collects a lot of information for data center facility managers. This was done in 2018, so this data is already getting old. But there really was no consensus about what today's range is. Many operators say a typical power rack density was between 5 to 13 kilowatts per square foot, but some were saying that some racks could consume up to 25 or even 40 kilowatts per square foot. So I simply did not have enough room on this slide to add more little black squares. So, okay, they use a whole lot of energy, but how does that energy breakdown kind of compare to that office space that we're most familiar with? So, no surprising, in our typical commercial office building, we're used to seeing between 30 and 40% of that load coming from HVAC. The next big thing on our list is lighting. Yes, keep putting in those LED lights. We got refrigeration, computers, office equipment, and so forth. And for a data center, as you can imagine, the server load, yes, is big, but the cooling load is just as big for that space. And to compare these two, take a look at lighting at only 2% compared to the large load of servers and cooling. And so this doesn't mean to stop installing those LED lights. Yes, we want to do that. However, don't expect lighting to really hold up your project for a data center. We really want to focus on that cooling and the server load to make a big impact. So to start off with cooling, I want to take you back to some of your first HVAC classes, our favorite, the psychrometric chart. I know there's a whole lot of lines on this chart, but I want to simplify it just for today's conversation in case you don't remember. On the x-axis on the bottom, you have dry bulb temperature, and then going vertically, we have humidity. And also, so when we look at ASHRAE and we look at occupied spaces, we're typically keeping our cooling within these two ranges. We have our summer cooling and we have our winter heating. And for these ranges, I know the numbers on the bottom are really small. So just to give you an idea of what we're looking at, winter typically ranges between 68 and 74 degrees Fahrenheit. Summer ranges between 72 and 80 degrees Fahrenheit with a relative humidity between 30 and 60%. And also, summer, going into a room that's 80 degrees sounds very hot, but you have to think about it also depends on location. If you're in the middle of the desert coming inside from an outside temperature of over 100 degrees, 80 degrees is going to feel very nice. Same thing for the winter. So now I'm going to change the chart to what kind of space a data center is looking for on this same chart. So I want you to focus in on the areas of the summer and cooling. So I want you to be able to notice the difference. Are you ready? It's really big. So we have our recommended space for data centers in that red area, but we also have the allowable spaces. These ranges come from the ASHRAE data center standards 90.4 comfort zones, if you will, for the data centers. And now you have to remember these spaces are not meant for people. They are made for servers. And even for facility managers of this space, sometimes it's hard to get that across. They also want to be comfortable in this space, but they use so much energy. So let's start with the center and move out. We have the recommended area, which is between 65 and 80 degrees. Relative humidity ranging between 20% to 70% relative humidity. Then those other areas that you see, A1, A2, A3, A4, those are dependent on the type of data center that you have. So A1 is typically for data centers that are tightly controlled environments, mission critical operations, and products that are like enterprise servers and storage products and all that kind of stuff. For the rest of the areas, A2, A3, A4, this is more for IT equipment, information technology. Some of the products that you would see and hear are like volume servers, storage products, personal computers, and workstations. Then the differences in the ranges between all of them kind of really depend on the products themselves and then also on like the age of the equipment. Older equipment, you're going to want to tighten those requirements, whereas some of the newer equipment and moving even into the future, they are getting even higher tolerances, so you can increase the temperature even more. There is also another class called an H1 class, and that has even a higher requirement. Those are for high density servers. But so I want to, since the recommended space is this red area here, I really want to focus in on that space because there's a lot of energy savings that can be had even in this space. So when doing site walks for data centers, this is where data center owners feel the most comfortable. This is between 65 and 72 degrees Fahrenheit, because a lot of times when you walk into a data center and it feels cold, the facility managers and owners feel like they are doing a great job. They think, oh, great, my data center is cold. I am making sure my servers are on and working and it is optimized. I have the best data center ever. However, even if we just move that yellow square over to the right, increasing the temperature just a little bit, it will save a whole lot of energy. And so remember, again, this upper limit over here is 80 degrees. And this temperature, you're probably asking yourself, okay, well, where am I measuring that temperature? This is the inlet temperature of the racks. We want to increase that temperature as close to 80 degrees as we can. And we can see dramatic savings. All right, so your next question, you're probably thinking, well, okay, increasing the temperature is great, but how does that affect the servers? This was an article, this data was from an article that was fairly recently published by ASHRAE in the ASHRAE Journal, March of this year, just a couple months ago, titled Data Center Energy and Capital Cost Considerations. And what this research article took a look at was potential savings with increasing that inlet temperature and free cooling, which we'll talk about more in a little bit, in different climates. It takes a step further by also looking at server reliability and IT equipment failure rates with increasing that inlet temperature. Now, to give you guys a baseline, during the first year that servers are installed in a data center, they typically have a failure rate of about 5%. While this might seem high, it often results from like out of the box defaults and initial configuration issues and stuff like that. But over the next couple of years, rates only rise at a level of about 1%. Which is fairly stable until around year 4, and then you're pushing up to around 11%. So given that, this graph that you see on here is the result of increasing that inlet temperature from 60 degrees all the way up to over 100 degrees. And if you remember from our psychrometric chart, the upper limit of that recommended range was around 80 degrees. And so we're really not seeing that failure rate increase all that much. So we know we're getting an idea of what we can do to increase efficiency in these data centers. But when we first do that site walk, it's always a good idea to benchmark. So I want to give you some resources on how you can do that. First off, PUE, power usage effectiveness, is an industry-wide term for data centers. It is the performance metric of data center efficiency, and it's a really simple ratio. Basically, you're just taking a look at the total facility energy over the IT equipment energy. And if you remember from the pie chart, IT energy and the HVAC energy is almost a 50-50 split. So with this simple ratio, you can get really quickly a good idea of how much energy your IT and your HVAC equipment is using compared to your overall data center energy. And then at the bottom, of course, you have your benchmarking metrics, what's typical, what's excellent, to give you that idea of where your data center stands. So this is the industry term, but ASHRAE kind of takes it a little step further. This is coming directly from ASHRAE standard 90.4. You have your annualized mechanical load component, or MLC, and this is the sum of your cooling, your pumps, your heat rejection fan, air handler energies, divided again by that IT equipment. Then you also have your ELC, or electrical loss component, And this looks at your electricity coming into the facility before going into the servers. So this doesn't take into consideration losses in the server energy, but rather the energy coming through your transformers, your PDUs, which we'll get into again a little bit more in a bit, and your UPSs or universal power supplies. Next, we have Energy Star. Of course, loves to compare you against existing data centers today, and they also use PUE. They just kind of take your actual PUE versus your predicted PUE, and then gives you a range between 1 and 100. All right, so we got our benchmarks now for our data center. So now let's take a look at some specific technologies by following our favorite friend, the energy pyramid. First off, we have conservation, and conservation focuses on removing that energy waste. And we just talked a whole lot about temperature. So one thing that you can see whether a data center has or not fairly easily is aisle containment and separating the hot air from the cold air. So typically you'll have a raised floor in a data center, and just like it's kind of showing in the picture, the cold air is being pushed underneath the floor through the front of the racks and then out the back of the racks. Then there's typically a roof over top, and in the picture you also see doors. And so that way it's really focusing all the cool air through the racks, pushing all that hot air out and recirculating through the system. Now, to give you an idea of how big of an effect that this can have, this was a site walk that I did on a data center that did not have aisle containment, but they were they were planning on putting in some aisle containment. So I just wanted to show them that, you know, validate their decision that, hey, you guys are doing the right thing, because take a look at what your data center is doing today. And I'll kind of describe the pictures. I know it's a little hard to see what you're looking at, but the picture all the way on the left is the back of some racks up against the wall. And so you can easily see all of the heat that's being pushed off the data centers onto the wall and up towards the ceiling where they have some cable organization. The picture in the middle is the front of some racks. And you can see actually the equipment on the top, I don't believe was on, whereas the other servers were. And that's just showing that the servers, while on, is pushing the energy through, but it was actually because there was no proper circulation, the equipment above was heating up from the energy from the adjacent servers. The equipment on, the picture all the way on the right is the back of the racks. And you can see there it's, you know, it's very spotty, it's very hot, and it is pushing all of the air out the back. But I'll show you what we should see in a data center. So this is an ideal image of what your data centers should look like. You can see on the floor, those are some grates where the cool air is being pushed up onto the racks and pushing the hot air where it wants to go anyway. And so you see a very nice gradient from cold to hot on your data center racks. So one type of technology that you can install if you don't have a very large data center, we mentioned that there's 3 million small to medium sized data centers in the US, and maybe they don't really have space to put in aisle containment. So these things can roll right in. They are cooling enclosures, and they have everything that you need inside for your data center, including fire suppression, which you can see in that picture on the right. And so these are awesome for small to medium-sized business because it completely eliminates all of those construction costs. In the picture on the left, you can see that there's a very large window behind that cooling enclosure. And, you know, typically in occupied spaces, people working in office space, they love windows. Let that sun come in and make you happy. But we don't want windows for a data center. That is just energy that we don't want. But with the cooling enclosure, everything is enclosed, so you don't have to worry about those windows anymore. You can just roll this in and your servers are happy, and your utility bill. These enclosures also range in size. They can be very, very small, like the other image, or they can get very large as well. So you can even put this outside of an office building. The next step in our energy pyramid is energy efficiency. So for this step in the energy pyramid, we want to, of course, increase efficiency of our systems by either replacing like for like, upgrading to a more efficient system, or improving the system with accessory equipment like economizers. However, I kind of want to focus on some things that are specific for data centers. So in our facility, we have CRAC, or I never know how to say this, CRA units, CRAC or CRAH units. The main difference being one uses refrigerant, the other uses chill water. You have a condenser for the CRAC unit, or you have a chiller and cooling towers for your CRA unit. Focusing on those CRA units, free cooling is one of the biggest things that are being pushed in the data center industry right now. Again, coming back to that psychrometric chart and increasing that inlet temperature. Well, if the outside air is cooler than your data center, let's utilize it. The free cooling system hooks up parallel with your chiller, and it can either work side by side with your chiller by pre-cooling the water coming in, or it can work instead of your chiller if it's cool enough outside for your data center. The next step in our energy pyramid is, of course, data management. And what do we do for data management? We optimize the building profile to avoid high costs through typically controls and software. So let's talk a little bit about that. Previously, I mentioned PDUs, or power distribution units. These are basically like really big power strips, but specifically for data centers and large loads. So they can be so-called dumb PDUs, like the ones you see on the left, or you can have smart PDUs, like the ones you see on the right. And how this helps you control your demand and power in the space. If you have smart PDUs, you're not just plugging into an outlet, you're actually able to log in and manage your power for your facility. So I was working with a customer, and one of our marketing efforts, we wanted to ask their customers, are you afraid to plug in? Meaning, are you afraid to plug in a new server because you might trip a breaker? Well, if you have a smart PDU to manage your load, you don't need to be afraid to plug in. The different colors you see on that smart PDU are relevant to the three phases that are coming into that facility. And so you're able to properly balance your load in your data center. Another method to optimize your demand is server optimization and performance. So just like any equipment, HVAC, fans, pumps, you have a performance curve. And I know you might be thinking, I don't want to touch those servers. Those are critical equipment for my customer. I don't want anything to do with them. And I understand completely, but I want to let you know that there are lots of other companies that do help with this and that specialize in servers and server optimization. So I want to encourage you to reach out to those third parties if you don't want to touch the servers themselves, because this software is getting more and more advanced. You're able to look at the capacity and load of each individual server, track its age and performance, so you're able to identify if you may have a problem before you have that problem, and that's critical for all of the facilities. Lastly, for demand management, we simply have temperature control again, input those variable speed fans, yeah, well, let's keep moving. I want to make sure we get through a couple of these slides here. Last but not least, we have energy generation. And for energy generation, I want to just mention that this was purpose. I put energy generation and not renewable energy, because at Itty Bit Better, we realized that every Itty bit counts. And I know this might sound corny and I'm just trying to plug my company, but it is so true, because though everyone's talking about solar and batteries, for data centers, it might just not be feasible. They need power, they need it now, and they need something to rely on. And so though data centers are still looking at solar and batteries, they still want those generators on hand in order to make sure that their servers can be up and running whenever they are. So as an energy engineer coming up, I was learning about solar, learning about wind, and all of these very sustainable solutions for customers. I had to refresh myself and learn more about generators, because they just, it's like if fossil fuels, you tend to want to avoid them, but this is what we need, and this is what can help continue to make our data centers just an itty bit better. So quick overview of some different fuel types. The most common for data centers are diesel and natural gas. And just to quickly go through some pros and cons, diesel, of course, we have a low purchase price and high efficiency, but we also have high emissions, and it requires large outdoor storage tanks to store that diesel fuel. However, on the other hand, natural gas, this connects to existing gas lines that they have already on site. It has the least amount of emissions over all of the fuels. It performs well in cold weather. It runs quietly. However, the generators typically require more maintenance. The generators typically are larger, and they have a shorter lifespan compared to diesel. The next option that I would typically recommend is a dual fuel generator. And the dual fuel typically can utilize either diesel or natural gas. And then, of course, you get the best of both worlds. You'll have lower emissions, and you can choose the less expensive option. However, these typically do have more maintenance, but with the savings of the fuel options, this is typically a pretty good option. Then comparing gasoline and propane. Gasoline is, of course, highly accessible and affordable, but we all know the price fluctuates a lot. And then there's also storage issues with it expiring after a year. And then, of course, it's very flammable. Propane, it does run quietly and cleanly, also compared to natural gas. However, it's more expensive, and it requires site storage, and it uses more fuel than diesel. So that gives you something to start with as far as generation for data centers. Last but not least, hang in there, we're coming towards the end. We have some further resources if you want to dive deeper into any of these topics. So we've referenced ASHRAE a lot. For data centers, it's ASHRAE standard 90.4 for data center energy. ASHRAE also has a TC 9.9. This is a reference card, and this references all of the psychrometric temperature and humidity ranges that I showed you previously. So the A1, A2, 3, and 4. Also, the Department of Energy, along with the National Renewable Labs, also have a website that have a lot of really great resources on it for data centers. It has a PUE calculator and a list of ECMs that you can reference for data centers. Personally, I go here a lot. It's a great resource to have. And last but not least, the Energy Star scorecard for data centers is that link down below for you if you want to screenshot this page. And that's all I got, John.
That was great, Anna. Thank you. All right, I'm gonna look through some questions. Let's see. Oh, good, you got a few here. All right, let's see. So the term, here's a question. The term PUE being total energy over IT energy, that means it's one if all your energy is coming from the IT equipment. If you reduce your IT equipment usage, then the metric would go higher. Well, I think you would reduce your, well, anyway. So the idea is that you want to reduce all your ancillary energy, so only the IT equipment is the major contributor. That was a question. Is that true? Does that make sense? Okay. Yeah.
Because the focus is on the data center itself. And so, oh, there you are.
Yeah, I'm sorry about that.
Yeah, so the focus is the data center itself. And so, yeah, kind of going back to that breakdown in the pie charts, you know, if you know what your IT equipment is compared to your overall energy, you have a pretty good idea of what everything else is using because it's so minor compared to your HVAC load.
So, I mean, what a question I came up with, which is related to this, is in the pie chart you showed us, you had, I'm making this up. So maybe you had, for a data center, you had IT equipment was maybe 40%, cooling was 40%, and maybe you had other stuff that was 20. I don't know, I'm guessing with that. But that's not a PUE of 2, that's a PUE of like 2 point something, isn't that correct? Because if it's, yeah, it'd be like 2.2 or 2.3, something like that.
Right.
Yeah, okay. Yeah, so I think another way of answering this question would be, you don't want to reduce your IT energy. I think mostly what you want to do is reduce your cooling energy usage or your HVAC energy or your lighting. I mean, one of the things that people do in IT centers is, you know, they leave their lights on all the time. Well, you know, especially in the big ones, if you have these aisles, you can put some of those lights on occupancy sensors or motion sensors. So they only turn on when people show up, and then they might be off for like a week or two at a time.
Yeah. I want to mention that, yeah, because I did a site walk, and what this particular site did was they had T-bar, and so you had your typical T-bar fluorescent lighting, but it was just a room that was retrofitted for their data center, and the way the T-bar was situated didn't provide very good lighting, and they had no way of turning it off. It was just on all the time. So what they did was add more lights. So they had these lights that were just on all the time, and then they had these lights with a switch.
I think that's typical. And what I found from going to data centers, they're never right. They're never right. It's like looking at an economizer. They're always not working. Not always, but I'd say like, you know, 60 to 80% of them aren't working right. Well, it's the same with data centers, and especially the hot aisle, cool aisle, or what you're calling containment. That they half do it. They kind of start it and then they don't ever finish it. And so one of the things with the whole idea of that hot aisle, cool aisle, or that's what I call it, the containment was, you know, you have cold air comes from the crack unit, it goes under the floor and it goes into this aisle, the cool aisle, and then it comes through the floor into the air, goes through the servers into the warm aisle where it's supposed to be sucked. You're supposed to have curtains that are going to, what's the word, separate the warm aisle and the cool aisle, so that hot air goes up into the ceiling, and then from the ceiling it comes back down into the crack unit. That's the way it's supposed to work, but it's so rare I see that. And what I see instead is, well, they kind of did it. They do have the cool air. They have the servers lined up with hot aisle, cool aisle. The air comes in through the floor, it goes in through the servers, but there's no curtain between the hot aisle and cool aisle up top. And so some of the cool air, you know, goes over into the hot air, or some of the hot air goes into the cool air, and up top it's all a mix. And then the air, it doesn't even go into the ceiling. It just they take air from the top of the room into the crack unit. It's like, it's just so common that yeah, data centers are easy.
Or I
The
love
hot aisle, cool aisle.
the extra standalone fans that they'll put in a room to just further circulate the air into one
That too.
section that's not getting enough cooling. And it's like, you're just adding more energy to the problem.
Data centers they're pretty easy. I mean, now I think about it, I mean, you need to know a few more concepts that you didn't know before. And like Hannah showed us, but really it's that hot aisle, cool aisle, and optimizing that whole concept, and then lighting, of course. But that is it. And it's almost everyone you walk into is going to be screwed up that way. Anyway, let's see. Sorry for that long diatribe. Let's find another question. Here's another question. How would you be implementing containment cooling for an IT closet? Very good. That is literally a closet with a Mr. Slim HP. I guess that means heat pump providing cooling. So I guess maybe that's just a split system. Is that what that is? A mini split system providing cooling. Yeah. That's a
yeah. So for the
no aisle here, right?
Yeah, for the smallest data centers, you're probably not doing much containment.
No.
Yeah, so whatever you can do probably helps. John mentioned some curtains, which is basically just like really thick plastic that hangs from the ceiling to help separate the hot and cold aisle. So like if you really wanted to get fancy with it, maybe there's something like that you can hang in the server room. But there's probably not much that you can do as long as it's moving from the front of the rack to the back of the rack. That's probably just your best option.
I have another comment on this that I guess I'm going to say it's controversial because I'm not 100% sold that I'm right. But if you try this in eQuest, you can prove it for yourself. So let's say you had a closet, a data center closet, which means there's a rack in there. One closet, they keep it at 60 degrees. Okay, the rest of the building's at 72. This room's at 60. The question is, are you going to save energy if you increase it to 78 or 80? And my answer is no. And the reason I say no is because let's say you keep it at 60 degrees. That room is cooler than all the other rooms around it. I'm assuming that this room is in the middle of the building. If there's no roof, there's no floor, there's no exterior walls, then that 60-degree coolness is going to filtrate out into the rest of the room. The rest of the building. There's no net gain or loss in cooling there. So and people, some people disagree with me, but you can just model it in eQuest and you'll see it's negligible savings to actually do that if it's just one room in the middle of a building. But I don't know. I mean, I may be wrong, but I'm pretty sure I'm right.
Yeah, no, that's something I was thinking about as well. The thermal images that I shared, that first one on the left where you can see the heat rising along the wall, you're absolutely right. That wall was adjacent to just some office space. And when I walked into that facility, there was nobody working that day, or at least nobody in the office. Everyone was working from home that day, and it was so cold in there. The thermostats were set to like 65 degrees, and now that hot wall is next to this really cold space where nobody's in. It's like, you're cooling this whole space. Just open the doors at that point to your data center and cool that too.
Yeah. So that's another thing I saw that was interesting is if you have a small like data closet, but it's by a window, so it's on the side of the building, let's say a south-facing window, and I've seen it. I've seen people do this. Then that's a different story. Then if you cool it to 60 degrees, well, you're losing all that cool energy through the window, and so then it matters. Or if there's a roof above it, then it matters. But if it's in the center of the building, it doesn't matter. You may save energy in that room by lowering or increasing the temperature, but you're going to then use more energy on the exterior or the outside of the room for the rest of the building, so it evens out. But anyway, I have another question. You talked about PDUs and metering, although you never mentioned transformers inside the PDUs. All the power flows through that transformer to the server, and it is a choke point for electricity. Additionally, you're cooling the heat from the transformer. Do you look at the low loss, high efficiency transformers? Who asked that? That's an interesting question. I don't know yet.
So I would say that that really kind of gets grouped into those ASHRAE metrics for like your ELC, the electrical loss components. That metric is really looking at the losses from your power factor, your large transformers for your facility, all the way up to that plug before the server. It doesn't take into consideration the servers themselves. But yeah, so you're absolutely right. If I'm understanding the question correctly, if you have old PUs, yeah, they're gonna get hotter, and so you're also cooling that load. But it gets to a certain point where there's only so much that you can do because you need that equipment in that space too. So upgrade your equipment. The newer equipment will produce less heat because it's more efficient.
Okay, I guess another question, and that is, so they say ASHRAE had these recommendations. Yeah, it should be whatever temperature below 80 degrees or whatever it is. Okay, but the question I have, and I don't think it's specific, or maybe it is. I bought some ASHRAE book and I read it a couple of years ago, and I don't think they were specific. There's a lot of different places you can measure this temperature. So I mentioned this to you already. So you can measure, is it the temperature that's coming back to the crack unit? Is it the temperature that the crack unit's delivering? Is it the temperature under the floor? Is it the temperature that goes into the highest rack at the server level, or the average of the highest racks at the server level? What temperature should we be looking at? I don't know if there's an answer to that, but it's
yeah.
Really
so yeah, for that psychrometric chart that we stayed on for a while, that's the inlet temperature of the rack. So when you're looking at the racks from the outside, I took those thermal images, it's that temperature on the face, the temperature of the air that's going directly into the servers. As close as you get it, we want to get it as close as we can to 80 degrees, ideally, to save as much energy as you can.
Yeah. Okay. So something that's interesting, I think it was the ASHRAE book I read, said that they had seen there was a problem with some building. I think it was in Seattle or something, and they moved all the servers outside. They moved them all outside and put them in a tent, and it was super hot. It was like 100 degrees outside, and they were still in a tent. I don't think they were cooling it at all, and they didn't have any failures. And so that's why, they can say, yeah, 80 is what we recommend, but it can, and you saw, I think you mentioned it, but it can handle 100, but 80 is what we recommend.
Yeah, exactly. And facility managers for data centers typically don't really understand that. Or just business owners in general. They want to walk into the data center and be like, look how nice and cool my data center is. They think if they walk in and they're sweating, then there's a problem. But really, I just want to nail this point home that these spaces are not cooled for people comfort. They're cooled for data centers.
That's right. That's exactly right. That's right. That's right. One last thing on your comment before, you said, yeah, the temperature we want, the temperature going to server, but the problem is that the server the temperature at the bottom of the rack and the top of the rack might be different by 10, 20 degrees. There might be a gradient. And so I think it's the temperature at the top of the rack. I think that's the temperature, the top rack going in. I think that would be my guess.
Yeah, I think it's more of like an average of how high you can increase that temperature, because it kind of comes back to the aisle containment. You're ideally what you're aiming for is to have consistent temperature along all of the racks, so all your servers are getting the same temperature.
That's right.
But if you're looking at the temperature at the bottom, that's 80 degrees, well, you're going to have a whole lot higher temperature at the top. So it's kind of taking an average. There is equipment, if you really wanted to get very specific in all of this, they have temperature sensors that you can get that are designed for data center racks, where you can just hook them on, and it's recommended you put one at the top, in the middle, and at the bottom, so you can see that temperature difference. And I mean, I haven't seen a data center with that level
I
of
have,
precision.
I
You
have,
have? Okay.
yeah, yeah, they have that.
Um,
The state of California
but
had that in one of their data centers.
but
Yeah,
yes, that would be ideal. But you know, as close as you can get it, that would be the best thing.
yeah, they had money and they had really good facility management there. Okay, here's one, and I can't answer this one for sure. Would power quality or reactive power reduction produce energy savings in the data center? Or would this go towards reduction of server failure rates?
Yeah, that's a great question. So that was something, actually, I was kind of going back and forth whether I wanted to include it in the presentation or not. So again, this would be grouped into that ELC metric that ASHRAE takes a look at. And there are a handful of technologies that target the power factor of the electricity going into the data centers. There's a few different types, and looking at how these systems works gets super technical. But you basically have two different types. You have like a static equipment, or you have dynamic equipment. So the static equipment kind of just looks at what the power factor is coming into the facility and then adjusts it accordingly. The dynamic system looks at the power quality that your data center is using, and then also what the power quality is of the electricity coming into the facility, and it dynamically adjusts the power factor to make sure that your data center is getting the best power. So that is another great energy efficient measure that you can implement for your data center. The equipment does get pretty expensive pretty quickly. So, you know, it all depends on your site and, you know, what you can do. And, but yeah, that was a great question.
All right, I think that's it for questions. Hannah, do you have any last words before we move on to the future?
I don't. Thank you so much for inviting me to do this webinar. I hope everyone got at least one thing from the presentation. Feel free to reach out anytime if you have more questions.
If I want to sum everything up, I'm really good at, I don't know if I'm good or bad at summarizing things and keeping it really simple. So the three simple things to find or to look for. 1, occupancy sensors on lighting. 2, raise the temperature set point. 3, that containment or hot aisle, cool aisle. It's usually not done very well. Learn how it's done, read on the internet how it works, and fix that. I think those are the 3 main things. Is there another, you know, if people just want to keep 3 or 4 things in their mind to look for, is there a third or fourth one you can think, or fourth one you can think of?
I think you got it. If it's got a window, just close it up. I keep seeing windows at data centers. Just close up that window.
Okay. Hannah, thank you. Thank you. It was a great webinar.
Thanks, John.